Welcome to the Walton Pi. Today I'm going to show you how you can show that two sets have different cardinalities. If they're finite sets, it's pretty straightforward, but if they're infinite or more complicated sets, we might not be able to just figure out how many elements are in each set and then go from there. So I'm going to show you two different methods of how we can show that sets have a different cardinality. As a quick refresher, two sets have the same cardinality if there exists a bijection from one set to the other. If it is impossible for there to be a bijection from one set to the other, then the cardinalities are defined to be different. So, if we want to show that two sets have different cardinalities, we have to prove that there is no bijection from one set to the other. Note that this does not say that the function that you chose isn't a bijection. That's not sufficient. We have to show that no function can be a bijection from one set to the other, which is more complicated than just showing that one specific function is not a bijection. Let's go through one example to show how we can demonstrate that two infinite sets would have different cardinalities. So we are going to prove that the integers have a different cardinality from the real numbers. So we are going to start by noticing that the natural numbers have the same cardinality as the integers. That is something that I've proven in a previous video, so if you would like to see that proof, go ahead and check that out. So if we can prove that the natural numbers have a different cardinality than the real numbers, then we have also shown have a different cardinality than the real numbers. So we are going to prove that there is no bijection from the natural numbers to the real numbers. We are going to do this by contradiction. So we are going to assume to the contrary that there is a bijection from the natural numbers. We are then going to show that this leads to some sort of contradiction. So since we're assuming that there is a bijection from the natural numbers to the real numbers, that means that we can list every real number in some ordering. So let's say that we've done that. So it looks like this. So this list is one way to represent our bijection from the natural numbers to the real numbers. So we have a 0th real number, a first real number, a second real number, and so on. Here we are going to be representing each of these numbers in their decimal form. So like n sub 0 is going to be, or the n terms are an integer, and then the d terms are going to be the digits. So if we were representing pi, then our n term would be 3, the first digit would be 1, second digit would be 4, third digit would be 1, and so on. So if we were to represent pi in the fourth position, n4 equals 3, d sub 4 comma 1 is going to be 1, d sub 4 comma 2 is going to be 4, and so on. I hope that clears up what this representation is representing. So in our subscripts for the d, the first number listed is the order that the number appears on the list. So if it's the 0th, 3rd, or 7th, or whatever real number, that is what that first number is representing. So our fourth real number is going to be represented by n sub 4, d sub 4, comma 1, d sub 4, comma 2, and so on. The second subscript is the order digit that it comes after the decimal. So it'll be like d sub something 1, then d sub something 2, and so on. So we are now going to use this list to construct a real number that is not listed anywhere. This is going to provide a contradiction because we had assumed that this was a bijection, meaning that every real number was listed. So if we can find a real number that was not listed, that tells us that our function was not surjective, which means that it is not going to be bijective. So if we look along this diagonal, that's going to give us the way that we can construct this number that is not going to already be in the list. We are going to construct it so it is different from every number at exactly, or at least one position. So if we go along the diagonal, we are going to be constructing something that differs from each of those digits. So to start, let's just change the n sub 0 term so that our number x starts with n sub 0 plus 1. That tells us that x is not going to be equal to the real number f of 0, which is our first entry in this list. We are then going to make it so it differs from f sub 1. And we are going to be doing that by doing what's called a digit change function. We do have to be a little bit careful though, because we can't just change everything to maybe the digit that's one bigger than it. Because then we might run into this sort of situation where we have repeating nines, because 0.99999 and so on is actually equal to 1. We have to be careful about having the digit 9 come up repeatedly. So we are going to define our digit change function like this. If the d sub kk value is equal to 3, change it to an 8. If it's not equal to 3, change it to a 3. The reason that we're doing this is just so that we are never running into the repeating 9 situation. We could have it so that everything goes to a 7 except for 7, which goes to anything but 9. That's pretty much our only restriction. We are just trying to avoid that repeating 9 situation. So, because every single spot is going to have some digit that's different, x is not going to be equal to any of these numbers that's already in the list, which means that it's always going to be different. So we have found, or specifically constructed, a real number that never shows up in the list. So since we had assumed that our function f was a bijection, that meant that every real number should have been in the image of f. But x was not in the image, which tells us that our assumption that f was a bijection was bad. It was not a good assumption, which tells us that no bijection actually exists, which tells us that the cardinality of the integers is different than the cardinality of the real numbers. We also have another situation that is going to follow a similar proof to the last one. We are going to have to construct something that should be in the image but is not. And this is going to be in our proof that shows that no set has the same cardinality as its power set. Again, this is going to be a proof by contradiction. So we're going to start by assuming that there is a bijection from a set A to its power set. And then we are going to construct an element of the power set of A which is not in the image of A. The set that we're going to construct is the set that I like to call the Barber set. That's not anything that is common or widely accepted. It's just a mnemonic that I use to help me remember how to construct it whenever I'm in a situation where I would need to prove something along this line. So the Barber set comes from what's called the Barber paradox. So imagine we're in some town, maybe it's the town of Seville, so we can have the Barber of Seville and laugh at ourselves for a literature pun in mathematics. But in this town of Seville, there are only two rules. The first rule is that there is one barber and he cuts everyone's hair. The second rule is that no one is allowed to cut their own hair. You might see a problem with this. There's one very difficult thing that we have to conclude. There's a paradox here. Who cuts the barber's hair? The barber has to cut everyone's hair, which means that he has to be cutting his own hair, but then no one's allowed to cut their own hair. So how does this work? Well, besides the kind of snarky answer where you say, well, the barber's bald, so he can't cut his hair, but he's also cutting his hair trivially. Besides that, we do run into this paradox. And this paradox gives us a hint as to how we might be able to construct something that would lead to a contradiction to saying that there is a bijection from a set to its power set. So, the barber's paradox comes from these two rules. 1, the barber cuts everyone's hair, and 2, no one cuts their own hair. These two rules are impossible to both be satisfied at the same time, assuming that everyone needs haircuts. We are going to then construct a similar paradox when we are dealing with the power set of A. So, we are going to be mirroring the two rules from the Barber's paradox to then be able to construct a Barber set, or something that is going to be behaving in a similar way to this paradox. So, the first rule for the Barber of Seville, or the Barber's paradox, is that the barber cuts everyone's hair. The similar rule in our proof is going to be that the function f maps to every element in the power set of A, namely that f is a bijection. We can also define a specific subset of A as follows. So we are going to call this the Barber set. So the Barber set B is the set of elements in A where A is not in f of A. So first off, we have to check, is this an element of the power set? So yes, it's only elements in A, so it is going to be a subset of A, and thus it's going to be an element of the power set of A. We also know it's going to exist because it is a subset. Like, it's not possible for this set not to exist. And this is going to be our rule 2. Let's go through a quick example of what B might be under a specific function f, and I'm not going to claim that this function is a bijection. For our example, let's say that A is the set 1, 2, 3, 4, and 5, and our function f from A to the power set of A is defined as follows, where f of 1 equals the set containing 1, 3, 4, f of 2 is the set containing 4 and 5, f of 3 is the empty set, f of 4 is the entire set, and then f of 5 is the set containing 2, 3, and 4. Now the question is, what is going to be the Barber set? What is B? Well, let's just go through and see which elements in our set A don't have themselves in their image. So if we look at A equals 1, we look to see, is 1 in f of 1? Well, f of 1 is the set containing 1, 3, and 4, so yes, 1 is an element of f of 1. So that means that 1 is not going to be in B. However, 2 is not in the set containing 4 and 5, which is f of 2, so that tells us that 2 is in the Barber set. Same thing for 3. 3 is not in the empty set, so 3 is going to be an element of B. But 4 is not going to be an element of B, but 5 is going to be an element of B. So we know that B is going to be the set 2, 3, and 5. Notice that this is going to be a subset of A, so it's an element of the power set of A, and specifically it's an element of the power set of A that is not hit by our function f, showing that f is not going to be surjective. Now, let's go through and use this to show how we can get our contradiction. So if we have our two rules, where rule 1 is that the function f maps to every element in the power set of A, and rule 2 is that the Barber set exists and is an element of the power set of A, can we see if we can spot how we might get a paradox or contradiction that comes from both of these rules being true at the same time? Take a moment, try and figure out what that contradiction might be. If you weren't able to figure out the contradiction, don't worry about it. It took me quite a while the first time I saw it too. So, the paradox or the contradiction comes if we ask ourselves, what element maps to the Barber set? So, if x is in A and x maps to B, the question is, can x be in the set B? We're trying to figure out what is B if there is an element that maps to it. So let's assume that x maps to B. Either x is in B or x is not in B. Because B is a subset of A and x is an element of A, x is either in B or it's not in B. So let's start by assuming that if x is in B, then that means that x is in f of x. So that's just saying that f of x equals B. Since x is in B, then x is in f of x. But that means that x cannot be in B. So that's going to be a contradiction. So that means that x cannot start in B. So that means we must assume that x is not in B. But if x is not in B, then x is not in f of x, which means that x must be in B, which means that we're also getting a contradiction there. That means that it's impossible for the Barber set to be in the image of f, which is always going to lead to a contradiction. Because for a given function, the Barber set is always defined, so the Barber set always exists. It's impossible for rule 2 to fail, which means that if we're getting this contradiction, rule 1 has to be what fails, which means that our function f wasn't a bijection. So that's where we are getting our contradiction. So we assume by way of contradiction that there is a bijection, then we define our Barber set, and then that shows that there can't be an element that maps to the Barber set. So that means that f is not surjective, so f can't be bijective. That means that the Barber set has given us a way to show that the cardinality of the set A has to be different than the cardinality of the power set of A. it's such a simple way to define a set, but it gives us such a powerful result. Like, we can look here. If we had assumed that something mapped to B in the power set here, so let's say that 2 mapped to B instead of mapping to 4 and 5, let's say that f of 2 is equal to the set 2, 3, 5. Well, then 2 is in f of 2, which means that 2 can't be in the power set of... that means that 2 can't be in the Barber set, which means we have to take it out, but now 2 is not in its image, which means we have to put it back in. We always get that contradiction when we are doing this, which tells us that the cardinality of A has to be different than the cardinality of the power set of A, which is a really powerful result. Because if we have an infinite set, so we have the natural numbers, the power set of the natural numbers cannot be the same cardinality, which tells us that we have to have different sizes of infinity, because otherwise every infinite set would be the same size, but the power set of an infinite set has to have a different cardinality. I hope this video was helpful and that the Barber set is as cool to you as it is to me. If not, just watch the video again. I'm sure you'll get there. Either way, best of luck with your math classes and your different goals of trying to understand math. If you'd like to watch some of my other videos, please check them out. It helps me out quite a bit. Please like and subscribe, as that helps me to be able to continue to make these sorts of videos. Best of luck and have a great rest of your day.